be like 5 or 10 minutes. I'm gonna come back in like 15 minutes, but just check to see if the red frame is on. Okay.
It's on? Like just the red frame?
Yeah, because it's recording now.
Every 5 minutes?
Not 5 minutes, but like every 10 minutes. Yeah.
Okay.
Yeah. I'm gonna come back like in 10 minutes, but just for now.
Okay. Oh yeah.
We should go to press this button again. The red one.
The red button?
Yeah.
Just once, right?
I think so. Just once if you see the red frame.
I'm gonna put my head over, bro.
Wait, you're on Sofa? Hi! I'll leave it on the floor.
That's the one over here. No, at least I
Watching the fucking game. If you're gonna watch the game, at least give me your spot.
Yeah, I think it should be fine.
Yeah, you're good. That's fine. It's recording. Okay. I told him to check it, so.
Right, guys, please listen to me. Whoever's outside, please come in. You can spread out here on the left. You can also occupy this first row. I'm sorry we don't have enough chairs. You might need to sit on the floor. I apologize, but this is the only room we could get. If you can please all tell everyone who's outside to come in, that would be awesome. Is there anyone outside right now? No? Yes, no, yes, no, no, yes. We're all good? Yeah, nobody's outside? Alright. Perfect. Guys, you can spread out here to the right. You can also take a front, please, if you want to. Alright, we're going to begin in a couple of minutes. So please spread out, take your seat. another chair. All right, perfect. Thank you so much. All right. Yes. No worries. Yeah, so I'll have one. Okay, no worries. All right. Perfect. Thank you so much. All right, let's begin. Welcome to MTL 200 midterm. Let me check the camera is working. 1 second. I hope so. Whatever. Okay, should be working. That being said, thank you so much everyone for coming. I didn't expect that many people. Actually, I should have, but I didn't have an option to choose a room or book a room. Everything is full. Chink school, midterms, exams, etc. Luckily, we got that. So thank you again for coming. I apologize for all of you guys for standing. Okay, it'll be a long study hall. So prepare, okay? All right. At the end of the study hall, I will share some questions from past year as well to prepare you how the midterm is going to be structured, what's going to be there. So far, basically, I'm going to talk a little bit about myself. Then I will go into the study hall itself. I'm going to talk about chapters. Usually, the way I structure the study hall for MTL 200 is not by just solving questions and doing some simple problems. I go into the content and I explain you the theory of MTL material science. MTL 200 is very much theory-based, okay? You need to learn theory. Your midterm is going to be full of multiple choice questions. There's going to be no long answer questions, full multiple choice, okay? So they might become tricky, okay? Very much depends. So you need to learn the theory. The best way to prepare to this course is by reading the book and attending my study halls, okay? I've been doing these study halls for the past 2 years, so this is my 3rd year. I got the TA position, teaching assistant position, in my 2nd year, right after finishing the MTL 200. So I was teaching MTL 200 in my 2nd year. And that was the first time I hosted the study hall. It was online, but good practice, okay? So this is first time I'm hosting the study hall in person. So I'm super excited, okay? That being said, a little bit about myself. I'm a 4th year aerospace engineering student. I'm also in the program of Accelerated Masters. I'm doing my Masters at the same time while I'm finishing up my undergrad. I am in the mechanical department doing Masters in material science. Okay, so I've been working in the material science lab at this university for the past 3 years, since my summer after the 1st year. Okay, I've had a chance to learn a lot about material science, and not just to learn, but to gain actual experience with casting metals, doing post-analysis, characterization, and working on research papers. So far, I've been co-authored in the 2 peer-reviewed papers. Okay, I've been working with my colleague, Dr. Bernoulli Andelop. It might be one of your professors. Somebody might have him for your MTL course as an instructor. I've been working with the gentleman for quite a while, and perfect. We're doing a lot of work. That being said, a little bit more about myself. You know, I founded MARS, Metropolitan Aerospace Rocket Society team, and it's been almost a year, actually a little bit more than a year from now. So that's a fantastic team. Everyone encouraged to join. Well, in fact, there's like already, the deadline was passed, so hopefully next year if you haven't done so. I'm part of MOC, Metropolitan Aerospace Combustion Hub. We're working on the bipropellant rocket engine. I'm a huge fan of student teams, and I do believe that student teams is the way to succeed in your undergrad. If you're only studying for your courses, that's great, but student teams is the only way to get a job after, okay? That being said, Anyone has any questions about anything before we start? Logistical questions? Yes, go ahead.
We found the study hall posted last year.
Yes.
I just wanted to know if this is similar at all.
It's going to be similar, yes. I'm going to be doing some extra practice questions, and I'm also going to be talking about the midterm a little bit. Okay? Yes. So, yeah, any other questions? No other questions? Any logistical questions? I'm going to be also posting the recording as well. Okay? All right, I guess we can start. Let me see what else I've discussed here. Yes, you need to read the book, guys. You need to read the book, Callister, 10th edition. This is the best book for material science, and this is your the only book they need to refer to in this course. Okay. I read the book twice. I remember in my year, it did help a lot. My study hall is basically full highlights of the book. So I'm telling you what you need to memorize, what you need to learn for your midterm, okay? But I highly encourage you to read the book. It is very important, okay? Blah, blah, blah. Yeah, so chapters 2, 3, 4, 5, 9. I didn't include chapter 2 in my study hall. Okay, so chapter 2 is pretty much easy. It's chemistry, grade 12. You need to read it on your own. Just about the electron shells and blah, blah, blah. Okay. What else we can talk about? Chapter 2, blah, blah, blah. And yeah, so make sure you pay attention during the study hall. I'll be talking about some things. I will also be inferring about the midterm questions that you will get, guys. So I'm not going to say which are the questions, but listen carefully. Okay. And I guess we can start right away. Okay, so chapter 3, the structure of crystalline solids. So the way I'm going to be doing things, I'll be writing on the board as well. Okay. And I'll be talking about the theory. I also have brought a couple of samples from my lab as well. You can take a look. The metal samples that I've been working on. Question?
Could you zoom in just a little?
Yes, sure.
Thank you.
No worries. So I will share those shortly. I'll be constantly referring to my experience so that you guys understand the application of what we're doing here. Because it's really hard to grasp essentially why do we need crystal structure? Why do we need Miller indices? Why do we need all those crystallographic planes and directions, etc.? Okay, so let's initiate chapter 3. Okay, so the structure of crystalline solids. Okay, every metal on Earth has a structure. Every component, every material has a certain crystallographic structure. Okay, in this course we talk a lot about metals, ceramics, which is going to be after your midterm. Hopefully, probably already covered it. You know, ceramics after chapter 9, I believe. Yeah, so here's an example of what the metal might look like. It's a perfect crystalline structure, which has some lattice and a unit cell inside. Okay, every metal obviously is comprised of atoms, right? So those atoms can be arranged in different ways. There are a lot of different structures that exist in this world, especially when we're not talking about the perfect crystal structures, when we refer to the structures which might be a little bit deviated from the typical ones because of their impurities or any other things that might be affecting the perfection of the crystal structure. On this figure, you can observe the unit cell, which is comprised of various atoms. Okay, so unit cell is the best way to essentially describe what is happening in your metal. Okay, I'm not sure if you've heard about like tensile tests, right? Hardness tests, but tensile tests is whenever you pull the metal and you observe if there are any stresses on the metal, right? Usually we tend to describe the stresses on the metal being imposed during the tensile stresses, referring to essentially the crystallographic structure, okay, of your metal. Because in one direction, your stresses might be bigger, but in the other direction will be weaker, okay? And Miller indices will be helping us with this, okay? So we're gonna refer to this as well. And so that's like the small background theory of why we need the unit cells. Basically, you know, material scientists need to communicate over the research papers and to other scientists what are the characteristics of the metal, why is it behaving this way, what are the reasons for it, and we refer to, you know, the unit cells and the lattices as well. That being said, lattice means a three-dimensional array of points. So essentially, lattice is basically an infinite amount of unit cells. Okay, it's infinite amount of unit cells, and unit cell is the smallest repeat unit of a lattice. Okay, so we can see an example of what the small unit cell might look like. Okay, so unit cell has a length of A that we refer to. Basically, the atoms might be located in different configurations. Okay, so essentially, in this course we discussed 4 typical metallic crystal structures. Okay, which are face centrocubic, body centrocubic, hexagonal closed plane, and simple cubic. You need to memorize this. Okay, you need to memorize FCC, BCC, HCP, simple cubic. Okay. So hopefully you've done your lab during the MTL 200 course, which you basically talk about various structures. Okay. Here I made a table summary of the things that you need to memorize. You will get multiple choice questions based on that, and perhaps some problems to solve. By the way, during the midterm, you will get problems that are not going to be like solving. You will just need to like solve briefly, put it into equation, the numbers, and then just find the answer. Okay. So some questions might be asking you like, what is the number of atoms in BCC or FCC? What is the coordination number? Okay. Anyone remembers what coordination number is? Okay, go ahead.
Is it like the number of neighboring atoms?
Yes, number of neighboring atoms. Yeah, so in FCC is going to be 12, and you can like visualize if you were to extend the unit cell in all directions, you would get basically 12 different atoms being neighboring one specific atom. Like for example, these atoms, and if you were to extend it, you would get the other atoms, and there's also the center atoms that are like neighboring with this one atom. Okay. You can guys Google like FCC structures. You will be able to visualize what coordination number is. I highly encourage to memorize these numbers. Okay, those are very important. Okay. Additionally, I encourage you guys to memorize what the elements correspond to which structure. Okay. Copper, aluminum are usually FCC. Steel is usually BCC, like iron. HCP is usually zinc, titanium, magnesium. Magnesium is HCP. And simple cubic, in this course, we refer to polonium as being simple cubic. Okay. Atomic pack and factor. Okay, we'll talk about this later, what the equation is, but it's basically how efficient your packing of a unit cell is. How efficiently you can put all the atoms in the unit cell to occupy all the volume of it. Okay? So as we can see, the FCC and HCP are the 2 most ones which occupy the most amount of area. The rest is just void. That is just void. Okay, so 0.68, and simple cubic is the least efficient crystal structure that we might get. Okay. On top of that, I encourage you guys to memorize what the lattice parameter is. So what is a lattice parameter? Lattice parameter is essentially the unit cell length. Okay, so we call it N. Okay, you can derive what this is, and if we were to basically write down the BCC crystal structure, okay, then we have one center atom. Okay, and we have corner atoms. Okay, like this, and like this. So every atom has a radius of r and diameter of d, which is basically 2r, r, and r. Okay, this is A, and this is A, and you can simply use the triangle identity. So 4r, basically all that square is equal to 2a squared. So 16r squared is equal to 16r squared is equal to 4a squared, right? And then we basically get, sorry, that's going to be 4. And then we basically get 8r squared is equal to a squared, so a is equal to root 2r, okay? So this is your lattice parameter, okay? Make sure to know how to derive it. When it comes to HCP, it's pretty hard to derive. I would not recommend, some people love deriving things during the final exams. I do love doing so, but for this guy, for HCP, don't spend time. Just memorize what the unit cell parameter is. Let me scroll down a bit. Okay. Beautiful. Okay. Yep. So, and again, simple cubic is just 2r. As you can see, it's just 2 radiuses of simple cubic atoms. Okay. Any questions on that? Yes.
Will we need to only know those elements?
Yeah. This is like even too much, but I recommend you to memorize those elements. Yeah. Like typically in this course, we refer to aluminum, maybe silver, iron, magnesium for sure, titanium, and zinc. Yeah, pretty much. So far, for the past 3 years, I've seen that being referred to. But yeah, I haven't seen the midterm, by the way, guys. I don't know what the questions perfectly are going to be. I I heard what those, like, some of those are going to be, okay, so I'm going to be, like, mentioning those, okay, during the study hall. All right, any other questions on this table? Should be pretty straightforward. Just make sure you memorize it, highly important. Okay, I'm going to move on. So atomic packing factor, as I discussed, we have the volume of atoms in a unit cell divided by total unit cell volume. So again, how efficiently you pack your atoms inside the unit cell. Okay. So for the density, okay, make sure you know this equation. Also for the midterm, you're going to be given equations. Okay, you don't need to memorize all equations, even though I highly encourage you to be familiar with all these equations. Last year midterm was you had basically at the end of your midterm, you had all the equations being provided. This midterm will most likely be like a question, and you're going to be given an equation right in the question. Again, don't quote me on this, but this is what I heard. Regardless, you're going to be given equations, okay? And you are encouraged to use them, of course, to solve the question. And density, you know, pretty straightforward equation. Make sure you know what that is. Okay, let's talk about a couple of definitions. By the way, all the definitions that I mentioned in this course, in the study hall, especially in this document, you need to memorize them. My PDF file, okay, basically is a shrinked version of the textbook, and I put all the things that you must memorize. But it doesn't mean you don't need to read the textbook. You need to read the textbook, okay? But if, I guess, you disappeared for an entire semester and before the midterm you came and you just read the PDF file, it's going to be really hard to get A+, but, you know, who knows? Highly encouraged to read the textbook, okay? Let's talk about the polymorphism, okay? Yes, so polymorphism is basically, let's say you have a structure, okay, a lattice, that contains various other crystal structures. So you might get like a metal, which contains on one, perimeter might contain FCC, on the other BCC. There are various reasons why this might happen, okay? So polymorphism happens in molecules, okay? So it's not just a pure compound. But allotropy, okay, this is where the crystal structures are different for a pure element. Let's say carbon, okay? Carbon can be essentially graphite, graphene, or can be a diamond, okay? So allotropy is when you refer to a pure element, like carbon, let's say, and polymorphism refers to basically a chemical compound, okay? So make sure you understand the difference, make sure you understand the definition. I remember a couple of years ago there was a midterm question about allotropy, and it was like saying what definition best describes carbon, okay? And carbon in brackets, it was like diamond, graphene, graphite. So, hopefully it tricks in your mind that whatever we discussed today is going to be about allotropy. Okay, so this is about that. We're going to move on. Yeah, we're going to move on. Question?
For the four crystal structures,
Yes.
for HCP, does the V unit cell only apply for HCP, or does it go for all of them?
Sorry, I'll go back. I have already understand your question. The
Like,
unit cells
the-
are
like-
all different for different crystal
Oh,
structures.
I
Yes.
see, okay.
Yeah, like you have, basically you have like, different, again, it depends on the radius, right? Like crystal structure is dependent on the radius of the atom. All atoms have different radiuses, okay? So you're going to be given a radius of the atom, and yeah, so hopefully that answers your question,
Yeah.
right? Okay, good. Okay, let's move on. All right, let's now talk about a very important topic, crystallographic directions and planes, okay? So I'm not sure how deep professors went into the discussion of planes and directions. You'll 100% get a question on this, at least one question. So let me talk about how you construct a direction, okay? On your midterm, you're most likely going to be given a picture. You're not going to need to draw anything. It's going to be like a picture, and then you, in A, B, C, D, define what is the direction, okay? So for the directions, we always use square brackets, okay? That's how we identify the direction. For example, there's going to be also a family of directions, so we usually use those brackets to define the family of directions. Basically, the family of directions is symmetrical vectors that can be comprised, like let's say the other way around, like 0, 1, 1. It can be go the other way around. It can also be shifted. It can also be up and down. So this is like a family of vectors in a way. Okay. So square brackets, and I also wrote down the approach how to do this. So you start from the origin. Okay. So let's say you want to go to 0, 1, 1 and find the vector for that or direction. You simply use Cartesian system. Okay. So you need to start from the origin. Okay. And I'm going to talk about the origins. They're very important. You need to have a skill to choose how and where to put the origin. I'll talk about it. Okay. So you always start, let's say, in this case, there are no negatives. So you start from the center. Okay. So you start from the center, 0. Then you go x 0. So you stay in the same location. Then you go 1 to y and 1 to z. Okay. And you draw your vector. Okay. It's pretty simple. You simply follow the previous coordinate. Okay. So that's how you do your directions. Okay. For example, this guy 0, 2, 1. As you can see, whenever you get numbers more than 2, this is going to end up outside of your unit cell. I do not recommend, guys, going beyond your unit cell. You need to stay within the unit cell. Okay, highly encourage you. Otherwise, if you start drawing the extra unit cells everywhere, you're going to like confuse yourself, and yeah, basically we'll get it wrong most likely. That being said, the way to do 0, 2, 1, you need to factor out the highest divisible number, okay, in your crystallographic direction. So you factor out 2, okay, then you're going to get 0, 1 half, 0, 1, and 1 half. Okay. So in this case, it's getting quite simple. So we're going to go 0, okay, so 0 in x direction, 1 in y direction, and only half of the unit cell in z direction. Okay. And again, just to mention, the unit cell has a length of 1. Okay, so you have a coordinate of 1, that means you travel up to the edge of the unit cell. Okay. Let's move on here. So we have 2 bar, 1, 2. Okay, so what does 2 bar mean? 2 bar means negative. Okay, so negative 2, 1, 2. Okay, if you were to analyze during the midterm what that means, I definitely recommend you to drop the square brackets, write down negative 2, 1, 2, factor out 2, you're going to get negative 1, 1 half, and 1. Okay, so this gets a little bit trickier, okay, a little bit trickier. You have a negative sign, okay, and if you do end up choosing this origin, you will have to go and leave your unit cell and build the second unit cell, okay? You will have to go basically from here to here, which is exactly the same vector as going from here to here, okay? So in order to avoid using and constructing different unit cell, you need to move your origin. You need to shift it, okay? So the best way to shift your origin is to first take a look which number is negative, okay? Which number is negative? So we see that the x number is negative, x coordinate, sorry, is negative. If it is negative, then you understand that if you start from here and you go to the other direction, because we always define this direction to be positive, then you will end up in a different unit cell. In order to avoid that, move your origin down here. So when you move 1 down there, you still stay within your unit cell. Okay? So this is kind of the rule of thumb to work with the unit cells, with directions, okay, crystallographic directions. Move down here, move your origin from here, and then simply follow your coordinate system. So we chose this to be negative 1, 1 half 1. So you go negative 1, you go 1 half, and you go 1. So you construct your vector. Okay. We have an example here, 3, 6 bar 9. So I'm going to go over here to write it down. We have 3, 6 bar 9. Okay. So the highest divisible number is going to be 9. So we put this out of our brackets. We drop the square brackets as well. We're going to get 1/3, negative 2/3, and we're going to get 1. Okay. So when you construct your unit cell, x, y, z. Okay. So let's construct the unit cell. Okay. And this is our origin. So for 3, 6 bar 9, we see that our y coordinate is negative. So this means that we'll need to move the y coordinate, we'll need to shift the origin to the edge of the y coordinate, so that when we move to the negative of y, we still stay within our unit cell. Okay, so our origin is going to be, I'll just redraw this unit cell like this. Okay, so our origin is going to be here now. So that's our point O. Okay, so we move from this origin positive 1/3 of x. We'll move here. Okay, so roughly 1/3 of x. Then we move to negative 2/3. So around here, 67% of whatever that is. And we move 1 up. Okay. So this is going to be our vector. Okay. So this is pretty much it. It's like directions are pretty easy to understand and follow. Yeah, anyone has any questions about directions? Any examples you want to do? Some crazy examples, but should be all pretty straightforward. Right? No questions? Question?
Do we just always divide by the highest number?
Yeah,
Always
so,
divide by the highest number?
yeah, so let's say you have, let me see, like 5, 10, 15, divide by 15, right?
Okay.
But if you have like 3, 7, yeah, you always divide by the highest number essentially, because you need to make sure you stay within fraction equal or below 1. Okay, because if you're not below 1, then you would need to go outside of your unit cell. Okay, yeah, so whatever that is, you're going to have the highest number divided by the highest number. Okay. Pretty much. Any other questions? Yeah, question?
Where can we find the PDF?
I will forward. I will send the PDF after. I'll have to modify it also a bit. Yeah, I'll upload it on my website. Oh, by the way, I didn't talk about my website. Talk about it later. I will also upload the recording on the YouTube and on the Muse website as well. So that's going to be there. This is working. Yeah, this is working. Okay. All right, let's move on to planes. Now it's going to be a lot of fun. Planes. Yes. Yes. Question.
So
Sorry.
for when you choose a direction,
Yes.
does it have to be on one of the edges of the cube, or can it be like at any point of the cube where you just choose the edge to
You mean the origin, right?
yeah, the origin?
Yeah. So it's preferably to choose the origin as your edge for the corner. The reason for it being it's convenient.
Okay.
It's better to choose so, right?
Okay.
Yeah, I haven't really experimented with choosing like somewhere within the unit cell. It makes sense to go like to the edge or the corner of the unit cell because it has a defined like point, right? Basically, it's not a fraction, nothing, right? It's just like 1, 1, 1 or 0, 1, 0 or 0, 1, 1, right? You understand what I'm talking about, right? Just it's convenient to do so. Okay. Right. Any other questions? Yes.
Just explain how the
Family of directions? Yeah. So for the family of directions, so you're most likely not going to be asked this question in the midterm, but for your understanding, the family of directions is, imagine you have this vector, right? But imagine you have this vector. Okay, they are the same, but it's just different, different origin and different direction. Like, like vectors, they have like the magnitude and the magnitude and the direction, right? So in this case, you can get different directions. But it also depends in which unit cell you are. You also might get something like this, something like that. There are also various other things, okay? I encourage you to read the book. It does talk about it a lot. Yeah, I don't really focus a lot about the family of planes or family of directions. It's just all you need to know pretty much. Yeah, and I also do have examples of what I, kind of offer to memorize for the family of directions. For example, 100. Callister textbook, I remember in appendices has various examples of family of directions and families of planes. Okay, so you can guys take a look if you're interested and have time. Yeah. Also, one thing. Let's say you were given a question about finding a coordinate in the unit cell. Okay, just finding a coordinate, and the coordinate might be just like 1, 0, 1. Okay, so you might get confused here in the midterm. It's going to be like in brackets, curly brackets, which refer to planes. Okay, but the question might ask you to find the coordinate. Okay, so yeah, don't stress out about it. It's just simply a coordinate. You follow the exact same strategy as for the directions. If it's 1, 0, 1, so you go 1, 0, and 1. So your coordinate is going to be right here. Okay, just to let you know, coordinates also exist. They're not really practical in material science, but just be aware of it. All right, let's move on to planes. So planes are the most interesting ones. Okay, so when we refer to in material science about which stresses go in which direction in the metal, or if we're talking about X-ray diffraction, which you might have done in your experiment, okay, about XRD. So the planes are what we refer to always. In some research papers, you might find some, some sentences which contain the brackets with some numbers, and they refer to Miller indices, okay, and they refer to specific planes. Okay, so I've also outlined here the approach on how to define a plane and how to draw a plane as well. The strategy is a little bit different compared to your directions. Okay, so for example, yes, we'll occupy this board now. I'll just do it here. Right. Okay, so let's say you have a plane 1, 1, 1. Okay, so let's say you were given on the midterm plane 1, 1, 1, and you were given A, B, C, D, various locations of where that could be. Okay, so the way you tackle that problem, okay, is you draw your unit cell. Okay, draw the unit cell. That goes down here, just a little road. Okay, so X, Y, Z. So origin in this case, as usually, in here. Okay, that's your origin. We don't have any negatives. So, question, yes?
Yeah, so for hexagonal closed pattern,
Yeah.
how would you suggest to draw the direction vector?
Okay, so don't worry about HCP. Okay, it's too complicated for the midterm. Like, I remember suffering doing HCP stuff for MTL 200. No. Don't do it, guys. Yeah, if you have time, you're interested, you can, yeah, so, oh god, okay. HCP, oh god, alright. Okay, that's crazy. You're punishing me. Okay, so, yeah. Yeah, no, I don't want to do it. Yeah. Good. All right. Coming back to planes, guys. Okay. Yeah, don't worry about HCP. It's like, okay. Are there like directions in HCP? There should be directions, right? Just formula indices, right? Yeah, that's painful. Whatever, guys. Let's get back to planes. Okay. So, for 1, 1, 1 plane. Okay. Thank you. So for 1, 1, 1 plane. Okay, the way to tackle this problem, we drop the brackets. Okay, we drop the brackets, and basically we have those Miller indices. Okay, so what's different about directions and planes? In directions, as I said before, you basically trace the previous what do we call it? The previous component. Okay, X or Y or Z. So you have 1, 1, 1. So you go 1 or 1, then you go 1, then you go 1. Okay? But for planes, you always go back to your origin. Okay? So you don't go 1, 1, 1 like in directions. For planes, you isolate all your coordinates, X, Y, and Z. Okay? You isolate them. So you go X here, go back to origin. Your Y is here. Okay? Then go back to your origin and go Z1. Is it clear? Okay. Decouple your coordinates. Do not go X, Y, Z, but go X, Y, Z. Okay. So that's very important. Okay. Make sure you memorize it in your head. Okay. So and the way we draw it clearly, there are 3 points. Hopefully you know, guys, from topology, in order to create a plane, you only need 3 points. You don't need 4 points. So this is going to be our plane. Okay. Cool. Yeah. So in my approach, I do say that we need to take the reciprocal, and yes, we do. The reason I skipped this step is because 1 over 1, 1. Okay. But let's say you had 2, 3, 1 as your plane. 2, 3, 1. Just randomly came up as this plane. What do we do? Take reciprocal. Okay. So we drop the brackets. That's the first step. You drop the brackets. Okay. So, do you guys see anything I'm writing? I guess you don't. I'll hold this up. Apologize. Hopefully it doesn't break anything, right? Oh. you're gonna give me random numbers. We're gonna draw some random planes. Okay. So highly interactive study hall. Okay. All right. Looks like a cube, right? Okay, very good. So we have x, we have y, and we have z. 2, 3, 1. 2, 3, 1. So what's the first step? Drop the brackets, reciprocal. Okay? We drop the brackets, take the reciprocal, 1 over 2, 1 over 3, 1 over 1.